This is Bhagyalakshmi. I'm working as Assistant Professor, Department of FME, Saint Martin Engineering College. Today we are going to discuss about new topic, that is differential equations and its applications. See, first of all, we have to discuss about the definition of the differential equations. See, definition: a differential equation is an equation containing derivatives one or more independent variable with respect to one or more independent variable is called the differential equations. See, we have some examples. Dy by dx is equals to 2xy. This is one of the example of differential equation, and another example, x into dy by dx is equals to y minus 1, and d square y by dx square plus dy by dx plus x is equals to 0. And these three are the examples of differential equations. In differential equations, another form also there, that is also we can read it as dou u by dou y is equals to minus dou v by dou x by dou y plus dou y by dou x plus 2 is equals to 0. Dou square u by dou x square plus dou square u by dou t square is equals to 2 into dou u by dou t. These all are the examples of differential equations. Now, here observe 2 points. We have eraser derivative and independent and dependent terms. So these two terms are very important. Observe this example. Dy by dx, inside what is dependent, what is independent. See, observe here, y is the dependent variable, here x is the independent variable. Okay, next let us enter into the types of the differential equations. Very important concept. Types of differential equations: there are two types of differential equations. One is ordinary differential equation, second one is partial differential equations. Ordinary differential equation definition is an equation containing only ordinary derivatives of one or more dependent variables of a single independent variables is called the ordinary differential equations. In ordinary differential equations, examples are dy by dx plus 5y is equals to e to the power of x, dy by dx plus dy by dt is equals to 2x plus y. Observe these two equations. Inside x is only one independent variable. In this example, inside t is the only one independent variable. That's why these two are the examples of ordinary differential equations. Next, to partial differential equations. In partial differential equations represented as PDE, the definition of partial differential equation: an equation containing partial derivatives of one or more dependent variables of two or more independent variables are called the partial differential equations. Examples of partial differential equations: dou square u by dou x square, dou square u by dou t square is equals to 2 into dou u by dou t. And another example, dou u by dou y is equals to minus dou v by dou x. It can be also written as dou u by dou y plus dou v by dou x is equals to 0. That is also the examples of the partial differential equation. Observe this example here. We have two or more independent variables. Here x and t are the two independent variables. That's why this example we can call it as partial differential equation. Now let us enter into the another new topic, that is order and degree of differential equations. See, first of all, what is order? What is order? Highest derivative of the differential equation, we call it as the order of the differential equation. Observe here, d power 4 y by dx to the power of 4 whole cube plus d square y by dx square minus 2xy is equals to 0. Here in this example inside order is the 4 and degree is equals to 3. See next one, next slide, next we have to discuss about the degree of the differential equations. Say the degree of differential equations, power of the highest order derivative term is called the degree of the differential equation. Observe these examples. Differential equations. First one is d square y by dx square plus 3 into dy by dx plus ay is equals to 0. Observe here highest degree to this order also 1, so that's why degree is equals to 1. Now second example, dqy by dx cube plus dy by dx whole to the power of 4 plus 6y is equals to 3. In this example inside order highest order is 1, that power is 4, so that's why we can call, we have to say it degree of this equation is 1. Next example, d square y by dx square whole cube plus dy by dx whole to the power of 5 plus 3 is equals to 0. In this differential equations, the degree is 3. The degree is 3. So this is about the degree of differential equation. Next we have to discuss some applications of the differential equations. Modeling with first order equations, Newton's law of cooling and electrical circuits. Next one, modeling free mechanical oscillations, no damping, light damping, heavy damping, and modeling forced mechanical oscillations and computer exercises or activities. Let us discuss one by one. First one, robotic industrialization. See, in this is one of the example of ordinary differential application of ordinary differential equations. See, automations and robotic electrolysis technologies for customized components, modules, and buildings. Prefabrications are based on differential equations. See, next one. Next application is population growth and decay. We have seen in section that the differential equations dnt by dt is equals to k into nt, where nt denotes the population at the time t and k is the constant of proportionality and serves as a model for the population growth and decay of insects, animals, and human population at certain places and duration. Solution of this equation is n of t is c e to the power of kt, where k is the constant of integration. Dnt by n of t is equals to k into dt. Integration both sides, then we get integration of nt is equals to kt plus integration c, as a is a constant, arbitrary constant. In n of t, integration n of t by c is equals to kt, or n of t is equals to c into e to the power of kt. C can be determined of if n of t is given at certain time. This is the equation of the growth and decay. This is one of the example of one of the application of differential equation. Now let us discuss one more application, that is examples of PDE. PDEs are used to model many systems in many different fields of science and engineering. Important examples. First one is Laplace equation. Second one is heat equation. Third one is wave equation. Let us discuss one by one example. First one is Laplace equation. See, Laplace equation is used to describe the steady state distribution of heat in a body. Also used to describe the steady state distribution of electrical charge in a body. Dou square u of x y z by dou x square plus dou square u of x y z by dou y square plus dou square u of x y z by dou z square is equals to 0 is the equation, Laplace equation. This is one of the application of the differential equation. Next application is heat equation. See, the function u of x, y, z and t is used to represent the temperature at time t in a physical body at a point with coordinates x comma y comma z. Alpha is the thermal diffusivity if is sufficient to consider the case alpha is equals to 1. This is a heat equation. See, dou u of x comma y comma z comma t by dou t is equals to alpha into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. This is a heat equation. This is also one of the application. Next, last equation, that is wave equation. See, the function u of x comma y comma z comma t is used to represent the displacement at the time t of a particle whose positions are at rest in x, y, z. The constant c represents the propagation speed of the wave. So this is the wave equation. See, we can read it as dou square u of x comma y comma z comma t divided by dou t square is equals to c square of dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. This is the wave equation. These all are the applications of differential equations. Next, let us discuss about the problems of first order differential equations. See, first order differential equations, let us solve one problem. First one, solve the first order differential equation 1 minus x dy plus 1 minus y into dx is equals to 0. This is the first order differential equation. Now we have to find the solution of this equation. Solution is 1 minus x dy is equals to this term sent to the right side, then it becomes minus of 1 minus y into dx. Here 1 minus x write down as it is. Here this term bring this side, then it becomes 1 minus y, 1 minus x upon 1 minus y is equals to minus for dx by dy. Now we convenient just interchange the LHS to RHS and RHS to LHS. Then dy by 1 minus y is equals to minus dx into 1 minus x. Now apply the integration on both sides. Apply the integrations on both sides. Then we get integration dy by 1 minus y is equals to integration minus dx by 1 minus x plus c. Here it can be written as 1 by 1 minus y into dy is equals to minus right outside of the integration minus integration 1 by 1 minus x dx plus c. See, it is in the form of, we know very well formula, integration integration 1 by x dx is equals to formula log x. So by using this formula, we can write it as 1 integration 1 by 1 minus y dy. We can write it as log of 1 minus y is equals to, here also same in RHS, here we get a logarithm of 1 minus x plus log c can also be written as log c. Observe here, log of 1 minus y, and this term bring this side, then it becomes plus log of 1 minus x is equals to log c. Here observe this, observe here, it is in the form of formula log a plus log b is equals to log ab. By using this formula, the above statement can be written as log of 1 minus y into log of 1 minus x is equals to log c. Observe here, both side log is cancelled. Then we have to write down 1 minus y into 1 minus x is equals to c. This is our required solution of the differential equations. Next we have to discuss one more problem. Problem number 2. Solve the first order differential equation. Solve the first order differential equation. First order differential equation. Differential equation is dy by dx is equals to under root of 1 minus y square by under root of 1 minus x square. Now solution of this equation, dy by dx is equals to, first of all we have to write down what is given here. The given that dy by dx is equals to 1 minus y square by under root of 1 minus x square. Now this one bring this side, then dy by under root of 1 minus y square is equals to, here denominator send that side, then dx upon 1 minus under root of 1 minus x square. Now apply the integration on both sides. Apply the integration on both sides. Then we get integration dy upon under root of 1 minus y square is equals to integration dx upon 1 minus x square plus c. Here c is a arbitrary constant. Next, integration dy by under root of 1 minus y square can also be written as under root of 1 minus y square into dy is equals to integration 1 by under root of 1 minus x square dx plus c. See, it is in the form, we know very well the formula, integration 1 by under root of 1 minus y square formula is sin inverse y is equals to integration 1 by under root of 1 minus x square formula is sin inverse x plus c. Finally, sin inverse y is equals to sin inverse x plus c also can be written as sin inverse c. See, this is our required solution of first order differential equation. Next, then we have to discuss one more problem, that is solve the dy by first order differential equation dy by dx minus y into tan x is equals to minus y into sec square x. This is a differential equation. Now we have to solve the solution of this differential equation. Dy by dx write down as it is here. This term sent to that side, then it becomes plus minus y secant square x plus y into tan x. See, again dy by dx is equals to just y tan x, write down first y into tan x minus y into secant square x. Now apply here, observe this equation. Here y is the common term, so write outside of this equation, then y into tan x minus secant square x, then y send this side, then dy by y is equals to tan x minus secant square x into dx. Now apply the integration. Now apply the integration on both sides. Integration on both sides. Then we get both sides. We get integration dy by y is equals to integration tan x minus secant square x into dx. See, the above equation can be written as 1 by y into dy is equals to integration, write down separately integration tan x dx minus integration secant square x dx. See, we know very well. Now I am using formula integration 1 by x dx is equals to log x. Again another formula also we know very well, integration tan x dx formula log tan x. Next, integration secant square x dx is equals to tan x. So apply these formulas in above statement, then we get 1 by y dx is equals to integration tan x dx minus integration secant square x dx. 1 by integration 1 by y dx, we can write it as log y. Log y is equals to log of tan x minus again tan x plus c also can be written as log c. C, this term this and this side, then logarithm log y plus tan x is equals to log tan x plus log c. This is our required solution. Now let us discuss about the more applications, some more applications on differential equations. Observe here the differential equation. First application is rate of changes. Rate of changes is one of the application. Next, weathers and climate, traffic flows, and financial water population also. Financial market, water population, and climatical change, suspension bridges, brain functions, and tumor growth. Next, robotic. Next, airflows across a plane's wings. Next, electrical circuits. Next, vibration of guitar strings or the some of the applications. Next, let us discuss what is the differential equation. We know already very well the definition of the differential equation. A differential equation involves the derivatives one or more dependent variable with respect to one or more independent variables is called the differential equations. See, the differentiate the here derivative means a rate of change. We have some examples. Dy by dx is equals to plus dxy is equals to e to the power of 2x. This is one of the example of differential equation. Here dy by dx can also represented as y dash, and here also dy by dx d square y by dx can also represented as y double dash minus y dash plus y square is equals to sin x, and these three are the examples, and this equation represent the notations of the differential equations. Next, we have to use vxy plus uyy, also another form of the differential equations. So this is the differential about the differential equations. Let us discuss another again we have to discuss some properties, uh, some properties, I mean type orders and degree of the differential equations. Let us discuss some example. Let us discuss some examples. First of all, types of differential equation inside the dy by dx plus 5y is equals to e to the power of x. Inside here, here dy by dx dt plus dy by dt is equals to 2xy. In this is the ordinary differential equation example. Observe here this differential equation inside only one dependent variable, one independent variable is there. So that's why this is a one of the example of ordinary differential equation. Next, partial differential equation inside always partial differential equations are denoted though. This is the symbol of partial differential equation. Here dou square u by dou x square, again dou square u by dou t square is equals to 2 into dou u by dou t. Here observe here one more example, dou u by dou y is equals to minus dou v by dou x also is the another example. Next, we have to find out the degree. Degree is the most important point. Now the degree, how can we find the degree of the differential equations? D square y by dx square plus 3 into dy by dx plus ay is equals to 0. Here observe here d square is the order. Here highest derivative is called the order. So highest derivative power is called the degree. So that's why this order is 1. This order is 1. So we can say it as very easily order always represented as order is always most important. First of all, so order is 2, highest power is 1, so that's why degree is equals to 1. Observe the second example, d cube y by dx cube is equals to dy by dx power 4 plus 6y is equals to 3. This equation inside what is the highest order, highest derivative here? Highest derivative is cube. So highest derivative is 3. Highest derivative is 3. So order is 3. Here 3 is the order. Order is the 3. Highest power so 1. So that's why degree is equals to 1. Next, third example inside this d square y by dx square whole cube plus dy by dx whole to the power of 5 plus 3 is equals to 0. This equation inside highest order is 2. So order is 2. Order is 2. So what is the highest order? How much here? 2. Highest power 3. Here 3 is the degree. But observe here this order 1 only, but highest degree, highest derivative here 1, but power is 5. Here 5 is not considered as the degree of the differential equation. Here 3 is the degree of the differential equations. This is about the degree of the differential equations. One more time explaining the definition of degree of the differential equation. The power of the highest order derivatives terms in the differential equation, that is the degree of the differential equation. Next we have to discuss about now we have to discuss about the orders and order and degree. See, order and degree of differential equation. This is the example of order and degree. Observe here, order is 4 and degree is 3. Here order is 2, not considered. The highest order is 4, so that's why we have to write order is 4 and degree is 3. Next we have to discuss again some applications. Modeling with first order equations and modeling free mechanical oscillations and modeling force mechanical oscillations and computers exercise and activities. These all are very important in differential equation applications. The applications are very useful in our real life. So differential equations is a very important chapter to discuss in engineering field. So thank you everyone.